So I'm happy to be here. I was here 4 years ago with everything that happened, and I gave a talk on foreign memory API, and it was an incubating API in Java 14, I think. And so I'm happy to be here now to talk about the foreign function and memory API, which is a finalized API in Java 20 in the upcoming Java 22 release. So why did we do this API? The main reason is that the landscape around Java application is changing rapidly. With the rise of machine learning, Java developers often need to do tasks that they necessarily didn't have to do before, such as talking to highly optimized linear algebra libraries that are not written in Java, but they are written in C, C++, or Fortran sometimes even. And the only way to reach to those libraries sometimes is just to reach into native code directly. So these libraries will not be ported in Java most of the time because they keep changing. So a new library pops up nearly every month with a new kind of idiom in order to do offloading of computation to the GPU. So how do we talk to native libraries in Java? We do that with JNI. How many of you have used JNI in this room? Okay, fair number, so good audience. You know, with JNI you can declare native methods. Native methods are like abstract methods in the sense that they don't have a Java method body, but they have a body that is defined somewhere else in a C file or a C++ file, and it can be C, C++, even assembly if you like to play with it a little bit. JNI is flexible, but it has a little bit of issues in the sense that it's what we call a native-first programming model. So it pretty much focuses on giving you access to Java functionalities from the native side of the fence. So when you write in JNI, you realize that quickly you are basically shifting all your computation logic from the Java world to the native world in order to minimize the number of transitions back and forth. And that can be a problem. There's also no, I guess, idiomatic way to pass data to JNI. Yes, you can pass objects, but that has an overhead. Sometimes a lot of developers end up passing longs as pointer, as opaque pointers that are stored in some Java objects, and that kind of works. So the problem with native function is, as I said, they never exist in isolation. They always have to manipulate some data, and this data is often off heap, of course. And there are not very many libraries in the JDK that allows us to do off-heap memory access. One of them is the direct buffer API. So probably you're familiar with direct buffers. They can be passed to native methods, and there are some JNI functions that allows us to, for example, get the pointer that is backing a direct buffer so that the JNI code can manipulate the buffer directly. One of the issues with direct buffer, perhaps the main one, is that there is no deterministic way to free or unmap a byte buffer. So if you are done using your off-heap memory, you basically have to wait for a garbage collector to determine that the byte buffer is no longer reachable from your application, and that can have a latency cost. There was also a problem in the addressing space. The byte buffer API was born in 1.4 time, so quite a few years ago, and we only use ints as offsets there, which means the maximum addressable space is 2 gigabytes. With -1, yes. With the advent of persistent memory, these limits are starting to be a little bit tighter. Also, there are not many addressing options provided by byte buffer. Either we go on the relative addressing scheme, where basically we say put in, and we rely on a mutable index on the byte buffer to keep track of where we want to store the bytes. But that's slow because we have to mutate some state, and then C2 optimization have a little bit more trouble coping with that. Or we go fully explicit, and so we put offsets everywhere in our code, and that makes our code a little bit more brittle. So this is what happens when you want to access a native library. You have a client, you have a native library, you have some JNI goop in the middle. What's inside the JNI goop? Well, a little bit of everything. There are some native method declaration in the Java code. Then if you compile this code using Java C-H, you have to use a special option which will generate the site headers file that you need in order to implement your C JNI function. So you go over to C, you implement your JNI function, you compile that function, that C file, with GCC or Clang, compiler of choice. you get back a shim DLL. This DLL is not the library that you wanted to talk to in the first place. This is just some extra glue code that you need in order to get to the library that you wanted. So now you have two native libraries, the one you want to talk to and the JNI DLL. And that's a little bit suboptimal. So what we need instead is a Java first programming model. So something that allows us to reach into native functions directly, only using Java code. We also need, since we want to model off-heap memory in a more sane way, we need a replacement for the byte buffer API, something that is more targeted at the use cases that FFI has. So we want deterministic allocation, we want bigger addressing space, we want better ways to describe track layouts so that we can access memory more easily. And also we want to tie everything together, so we want to define tools that allows us to automatically generate bindings for native library in one shot. And we'll see a little bit about that later. Ultimately, our goal is not to replace existing frameworks such as JNA, JNR, for example. I think Charlie is going to talk about that maybe later. But to help some of those frameworks to overcome the workarounds that they have to keep doing all over again, because they don't have a proper API to deal with pointers, they don't have a proper API to free pointers when they are no longer used, and so hopefully some of this stuff is going to come handy in those cases too. So Panama is not just about the foreign function and memory API. Of course, that's a huge part of Panama, but Panama also contains the vector API, which is an ND API to access SIMD computation from Java code directly. But there's also Babylon, a project that recently sprang up, which allows us to see what's inside the body of a Java method with a nice IR that can be introspected using Java. So what can you do with Babylon? For example, you can take a Java method that contains a loop, for example, and you can inspect that loop, you can turn it into a GPU kernel, and then you can use FFM to dispatch that kernel using CUDA to the GPU. So Babylon and FFM kind of comes together and provides us a better and more robust solution in order to do on GPU computing. The main abstraction when it comes to accessing memory is called memory segment. That gives us access to a contiguous region of memory. There are, of course, two kinds of memory segments. This is similar to byte buffer. There are heap segments that are backed by on-heap memory, and native segments that are backed by off-heap memory. All segments have a size, so if you try to access a segment out of bounds, you get an error. They have a lifetime, which means they are alive, but then after you free them, they are no longer alive, so if you try to access them when they are no longer alive, you get an exception. And some segments may also have confinement, so they may start in a thread and they can only be accessed in the same thread where they started from. How do we use segments? Well, it's not too difficult. It's very similar to byte buffer. You can almost see the translation, the mechanical translation from the byte buffer API to memory segments. Let's say that we want to model a point that has fields x and y. So what we have to do, we have to allocate a segment. We do that using an arena. We will see a little bit later what an arena is. But let's just go with me for a minute. We have to allocate a segment with 16 bytes because the coordinates are 8 bytes each. And then we put double values into each coordinates, one at offset 0 and another at offset 8. And that's how we populate the memory of that particular segment. So one of the issues that we have in this code, of course, is that we are using an automatic arena. An automatic arena is essentially providing an automatic deallocation scheme, which is similar to the one that is used by the byte buffer API. So we are not going to get any advantage here, but we can do one better. In fact, this is actually where we spend the most time designing the memory API. Java, as you all know, is based on the very idea of having automatic memory management, which means you only care about allocating objects. The garbage collector will sit behind your back and automatically recycle memory when no longer used. This is based on this concept of computing which objects are reachable at any given point in time. Problems with this approach is that computing the reachability graph, so which objects are reachable at any given point in time, is a very expensive operation. And you can find that garbage collectors especially the one of the latest generation, the low latency garbage collectors, they don't want to materialize the reachability graph as often. So if you try, for example, to allocate a lot of direct buffer using ZGC, you will see that there's a lot more time before the byte buffer is collected compared to having something else where you can actually deterministically release the memory. So that's a problem. Another problem is that the garbage collector doesn't have knowledge about the off-heap memory region that can be attached to a direct buffer. The only thing the garbage collector sees is a very small instance, a very small byte buffer instance that is like, I don't know, 16 bytes or something more, but it doesn't see that maybe there are 4 gigabytes of off-heap memory attached to that, so there's no way to prioritize that collection. And also, garbage collector only can keep track of an object as long as if it's used from a Java application. So if that byte buffer escapes to native code, then it's up to the developer to keep that object alive across the native code boundary. So you have to start playing with reachability fences, and your code suddenly doesn't look as good anymore. So what we need is a new way to think about managing memory resources explicitly. And that's challenging because we are sitting on top of a language that made its success on the very idea of basically never worry about releasing memory ever, because the garbage collector will do it for you. So what we introduced was an abstraction called Arena. An Arena models the life cycle of one or more memory segments. All the memory segments that are located with the same Arena have the same lifetime. So we call this a lifetime-centric approach, because first you have to think about what is the lifetime of the memory that you want to work with. Then you create an arena that embodies that lifetime, and then you start allocating memory. There are many kinds of arena. Of course, there is the silly global arena that you can use, and basically whatever you allocate, it stays alive, is never collected. There's the automatic arena, which we saw before, which basically gives us an automatic memory management scheme, which is similar to the red buffer. But then there are the more interesting confined and shared arenas. These are arenas that support the auto-closable interface. So if you call close on that arena, all the memory that has been allocated with that arena will basically just go away deterministically. We don't need to wait for the garbage collector to do that. There are strong safety guarantees. Regardless of whether you are in the confined case or in the shared case, it's not possible for you to access a segment after it has been freed. And in the shared case, we had to do a lot of JVM black magic in order to make this work. Because, of course, you can think, well, we just put a lock. Whenever you access a memory segment, we'll check whether the segment is still alive using an expressive operation, and then you realize that memory access is like 10x slower than before. So what we did instead is, with the help of the GC team, we relied on some safe pointing mechanism to make sure that it is never possible to close a segment while there is any other thread that is trying to access the same segment. That works very well. Of course, it's a little bit more expensive if you need to close shared arena very frequently, but hopefully you won't need to do that. So what we are trying to do here is to find an happy balance between the flexibility of C automatic memory, deterministic memory management, where you have to do free and malloc explicitly. That's very flexible, but it's also very unsafe because you can have use after free, you can have memory leak, or the extreme safety of Rust, which comes at the expense of some flexibility when you try to code. Because if you want to do, for example, cyclic data structures in Rust, like a linked list, it becomes very, very, very difficult. So Java is trying to sit in the middle, and I think we've done a good job doing this. So how do you work with explicit arenas? It's basically the same as with automatic arenas. The only difference here is that now we are using a try with resource statement. So we create the arena inside the try with resource block. We do the allocation, we populate the point struct, and then when we close the brace, all the memory goes away. So this is much better than the direct buffer counterpart, especially if you need to frequently allocate off-heap data structures, because we no longer put load on the garbage collector just to clean up the off-heap memory. So one thing that we need to still improve on this API is how do we access the fields of the struct that we want to operate with. In the example that I showed previously, we had to say, well, I want to access offset 0, I want to access offset 8, because we knew these were the offset where my fields are. But what if we could just declare what is the layout of the struct that I want to work with. What if we can translate the struct point2D definition that we have in C into some into a Java object that models the same layout? Then we can start asking interesting questions, such as what is the layout of the field X or Y? Give me a varendo for accessing the X field. And that's exactly what we are doing here. So instead of just relegating the definition of point2D in a comment, we actually define the layout of the point struct as an object, as a Java object, and then we use this object to derive the two varendos, one for accessing the X field and one for accessing the Y field. Then inside the try with resources, we can just use the varendo to access the field. So we don't have to specify the offset 8 for the field Y, for example, because the varendo will encode all the offset computation automatically. At the same time, look in the allocation expression, the very first, inside the try with resource block, we can see that we are just passing the layout to the allocation routine. And the layout, of course, knows what is the size of the block that we want to allocate. So switching gears a little bit, let's start talking about FFI. The main abstraction in FFI is called native linker. This is an object that essentially embeds the calling convention of the platform in which the JVM runs. It provides two capabilities. The first is it allows us to derive a method handle that targets a native function. So we can basically describe the native function we want to call, get a method handle, and just call it from Java. The second capability is kind of the reverse of that. So we have a method handle that describes some Java computation. We want to turn it into a function pointer, so a memory segment, that then we can pass back to native code. This approach is inspired to, for example, Python C types or libFFI. These are kind of the main inspiration. So we want to be able to describe a C function from Java so that then we can call it directly. It all builds on the abstraction that we've seen so far. So we use layouts to describe the signature of C functions. We use memory segment to pass addresses or structs, and we use arenas to model life cycles of app calls and to model the life cycles also of loaded libraries. So when we want to call a native function, so here I define a function distance that takes a point and returns the distance of the point from the origin. Actually, doing that in C is a little bit more convoluted than it looks like, because it essentially depends on the platform we are on. So if we are on Linux, we will have to look at some rules that are called the sysv calling convention, and that tells us that, for example, structs that are as big as the point2D struct that we have here can have their fields pass in register. So the only thing that we need to do when calling the distance function is to load the first floating point register with the value 3, the second floating point register with the value 4, then we just jump on the function. But if you are on Windows, even if you are on x64, but on Windows, there is a completely different set of calling convention, which actually tells us that any struct that is bigger than 64-bit, such as our struct here, will be passed in memory instead, which means the struct has to be spilled on the stack, a pointer to the stack has to be stored in the RCX register, and then we jump to the function. So same function, same architecture, because it's x64, completely very different set of assembly instruction that needs to be generated in order to act as a trampoline from Java code, for example, to C code. So that's why it's important that we are able to describe the signature of a C function to the linker, because the linker then will inspect the signature of that C function and will determine what is the exact set of instruction that we'll need in order to go from the Java call to the native code underneath. And so how do we do this? Well, when we call the down call handle on the native linker, we will pass, of course, the address of the function that we want to call. This is obtained using a symbol lookup, which we won't have time to investigate in further detail, but it will basically give us the address of where the distance address function lives. And then we provide a function descriptor. This function descriptor is nothing but a set of layouts, one for the return type and one for the argument. In this case, we know that the return type is double, so we use a double layout. And the argument is actually the point2D struct that we defined before, so that same layout can now be reused in order to describe the signature of the function. Then inside our try with resource, we populate the point as before, and then we can call the method handle. So we just pass the point memory segment to the method handle that we obtain, and that means that we will be able to pass the point by value to the C function. And nothing else needs to be done, because the linker will figure out exactly what set of machine instruction to generate in order to go there. So, of course, when we talk about native function, we always have to keep safety in the back of our mind, right? Because whenever we go into native, the operation is fundamentally unsafe. We could, for example, make a mistake in describing the signature of our target C function, which means the assembly stub that we have is not correct for calling that particular function. We may cause all sorts of issues. The foreign code may attempt to free memory that has already been freed from Java code. Or we may get a pointer from native code. We may try to resize the pointer, but we got the size wrong, and so we are suddenly trying to access memory that is not there. So in the FFM API, there is a concept that is called restricted methods. So there are some methods in the FFM API that are not directly available all the time. They are part of the Java C API, so if you go in the Java doc, you can see them. But they are restricted, and you need to use an extra command line flag if you want to use them without warnings. So for now, basically, if you try to use a restricted method, such as the method for creating a down call method handle, you will only get a warning. But in the future, we plan to turn this warning into an error, and in that case, you will have to use a new option that is called -- enable native access, that will grant a subset of the modules of your application, or the all unnamed module if you're using the class path, access to restricted methods. This is a part of a bigger plan to move Java on a more solid foundation, one that allows us to provide integrity by default. So Java in its default configuration should always preserve integrity, which means it shouldn't be possible for native code to mess up with things, with invariants such as, for example, mutating final fields and things like that. So this is the workflow using FFM API when we want to access a native library. So we still have something in the middle between us and the native library that we want to call. This time, though, the stuff we have in the middle is just Java objects. We have memory layout, var handles, method handles, function descriptors. But here's an idea. What if we could generate all this stuff mechanically using a tool? And that's exactly what the jextract tool does. So let's say that we want to call the qsort function, which is actually a tricky function because it has a function pointer that allows us to sort the contents, to compare elements of an array. So it uses a function pointer type def. So if you want to model this using plain FFM, it's going to take you a little bit of setup code in order to create the upcall stub and the method handle that are required to call this. But if you give all this header to jextract, so we call jextract, we point it at the header, the standard library header where this is defined, then we basically just get a bunch of static declaration that we can use to call qsort. So if I do all this, the only thing I have to do from my code is first to create the function pointer, and this is possible with a factory that has been generated by jextract that allows me to pass a lambda expression, and the lambda expression will be turned into a function pointer that is stored inside a memory segment that then I can pass to the qsort function. And the qsort function is not a method handle anymore. It's a nice static wrapper around the method handle, so it's much better to use from the Java developer perspective, because using method handle can sometimes be tricky with the fact that we can pass the wrong type and then it gets lower and things like that. So in comparison, this is the code that you had to write if you wanted to do this using JNI. So there's a Java code with native methods, there's an header file that is generated by Java C, and then there's quite a bit of C implementation in order to do qsort, and it actually took us a few attempts in order to get to the best optimal implementation, because our first attempt wasn't very good. It can actually get quite tricky. And even better, if you look at the performances, the plain FFM-based approach is roughly 2x, 3x faster than the JNI approach, heavily optimized JNI approach. And that's because a colleague of mine, Yor Vernet, has put a lot of effort in trying to optimize, especially the upcall path. So when you want to call a Java function from native code, there was a lot of performance left on the table from JNI, and we were able to greatly improve the performances there. For regular calls, you probably won't see much difference. So FFM is more or less on par with JNI, but as soon as your native call is starting to upcall back into Java, you're going to see massive differences. So wrapping up, FFM provides a safe and efficient way to access memory. We have deterministic deallocation, we have layouts to describe structs, so it gives us ability to describe the content of the memory that we want to work with, and then get variables to access that memory in a much more robust way. Then we have an API to access native function directly from Java, so no need to write JNI code. That means that your deployment gets simpler because you don't have that shim-DLL going around that you need to distribute along with your application. And together, the foreign linker and memory segment and layouts provide the foundation of a new interop story for Java that is based on a tool called jextract, which allows us to target native library directly. One thing that emerged while we were working on FFM is that there's quite a lot of number of use cases that we didn't anticipate at first. Since FFM is a fairly low-level library, it allows very easily for other languages that are built on top of the VM, such as Scala, Clojure, or even Ruby, JRuby, to use the FFM layer to then target native function. That was very expensive to do with JNI because it meant that the other language sitting on top of the VM needed to spin some JNI code in order to be able to do that, or maybe uses a library like libffi. But with FFM, this is possible directly out of the box. And I think that's a good improvement. We have been incubating and previewing, of course, for a long time, so since JDK 14 essentially. So that allowed us to get a lot of feedback from Apache Lucene, Netty, Tomcat, and I think today they are in production with some of this stuff. So I think if you run Lucene with Java 21, you are getting a code path that uses FFM under the hood, and I think that helped them to get rid of some of the issues where they had to use unsafe in order to free the memory that was mapped, because otherwise waiting for the garbage collector could lead to other issues. We also are being used by Tornado VM, so in that case it's an interesting case where memory segments are used to model memory that is inside the GPU. So they're using memory segment in a very creative way there, and a bunch of other projects has chimed in as well. So that was for us, it was a very successful experience of using preview features because it allows us to gather a lot of feedback. Not necessarily we have a lot of knowledge on these topics within the JDK team, so it was good for us to put something out and then hear how people were using some of this stuff and make it better. That's the end of my talk. These are some of the links. I hope that you are going to try FFM in 22. You can subscribe to the mailing list and send us feedback. There is a link to the jextract tool, so there are binary snapshots available, so you can grab the latest one and start extracting your library of choice and play with it a little bit. And then a link to the repos, but that's mostly it. Thank you very much. Questions? Yep.
How is FFM compared with Kotlin native, which has some similar aspects? I mean, in the API context, of course.
I think it's basically what is the difference between these and Kotlin native, since Kotlin native can provide access to off-heap memory and native function as well. I think they are kind of very similar. One of the things that I think Kotlin native cannot do, because it's still sitting on top of the VM and it has to play by the rules of the existing libraries, is that it cannot have a solution for releasing memory safely. So I believe that Kotlin native is going to use some, it's going to say at some point, oh, if you use pointer, your code is going to be unsafe, and you try to free a pointer, then all bets are off. So this is the main, with our solution, if you use memory segments, you can close an arena and your code will never crash. You may get an exception.
This is the same thing with Kotlin native. I don't know if they call the arenas, but it has the same thing.
Yeah, but in all the APIs I've seen so far, there's always like, if you use them correctly, it works, but there are ways to use them for multiple threads where it stops working, unless you go deeper at the VM level, of course, which, of course, Kotlin native cannot do.
Up here, Maurizio. Go
Hey.
on. Question. Maurizio, up here.
Do you know how many platform-specific hacks need to be done? Like if I want to use one code on like ARM, macOS, and Linux RISC-V or something, or is it all fully one code for all platforms?
So, in terms of jextract, the model, sorry, the question was, how platform-specific is all this? Do we need to worry about differences between platforms? The answer is yes, in the sense that the jextract tool is going to give you a binding for the platform that you're running on. Now, this sounds scary. In practice, for example, if you work with a high-level library such as libclang, for example, we have a single run of jextract, and then we reuse it across all the platform, and it works fine, because that library is defined in a way that is portable. If you work with system libraries, of course, you're going to have a lot less luck, and that system library is only going to work on one platform, and other platforms will need to do something else. Yes. Oh.
Yes. Can you tell us about the memory footprint compared to JNI?
Memory footprint compared to JNI. So, of course, if you use memory segment, there is a little bit of footprint because you have an object that embeds an address, so you don't have a long. But our plan is to make all these memory segments scalarizable, because the implementation is completely hidden. You only have a sealed interface in the API, which means all these interfaces are going to be implemented by value classes when Valhalla comes, which means if you bring up a memory segment out, you wrap a memory segment around an address, you're not going to pay anything allocation-wise. For now, there is a little bit of cost in the cases where the VM cannot figure out with escape analysis the allocation. But in the future, we plan for this to completely disappear.